Hey guys, here is me explaining the notes that I have uploaded. And like I said in the write up, this week being more on Power Series and Taylor Series, it really is about tricks to help us develop Taylor Series much more rapidly. And so let me show you what I mean by that. We should know by now that this is the Taylor Series for e to the x centered at 0. Now, what if we wanted one for e to the x squared? Well, I know that e to the x squared is nothing more than e to the x, where I replace x with x squared. You can see it's right here. And so all I did was where the x is, I replaced it with x squared, and then I just figure out what that is. And so a power to a power you would multiply, and so it would come out to be n equals 0 to infinity x to the 2n over n factorial. And that you could do the ratio test on and figure out its interval and radius of convergence. And everything works out fine. The next type of series, so that just goes to show that sometimes if you knew a base Taylor series and you're just manipulating through algebra, like the variable in there, you can actually just manipulate it in the statement of the original function's Taylor series. We also know then that a geometric series looks like this, and we know when it converges. So, if we take a to be 1 in this case, then it comes out to be 1 over 1 minus r, and it's still the same conditions because the r is what sets it. The a has nothing to do with where it does and doesn't converge, because that a just pulls out front and can be a scalar out there. So what about a Taylor series for 1 over 1 minus x? Well, if you look, 1 over 1 minus x looks a lot like 1 over 1 minus r, where all I do is make x be r. So if I made x be r, if I made that be x in the statement, it should be the Taylor series for it. And furthermore, if I put an x where r is right there, I would know that it converges between -1 and 1. And so let's see that come out. So here's what I just said on the other page. Here is me substituting the r for the radius of convergence in the interval, and then that gives me it in an inequality form. If we wrote this out, it would be x to the 0 is 1, plus x to the 1 is x, plus x to the 2 is x squared, and that's what it would look like. But this tells me the radius of convergence is 1, and the interval of convergence is -1 to 1. On this, I didn't check in here, and I just put parentheses, and I didn't, you have to check the endpoints to see. But look at this, you guys. If this is 1, then you're just going to do 1 plus 1 plus 1 plus 1 plus 1 plus what forever. That's going to add to infinity. So it diverges at 1. And if you put -1 in, -1 to the 0 is 1. But -1 to the 1 is -1. And then -1 squared is 1 again. So if we put a -1 in there, it would really be 1 plus -1 plus 1 plus -1 plus 1 plus -1. And in there, the sum would go 1, but then when you have 1 plus -1, now the sum's 0. And then when you add 1 again, the sum's 1. And then when you add -1, the sum's 0. And if you never stop doing that, you don't know, does it add to 1 or does it add to 0? And so by the divergence test, though, both of those work because the limit as n goes to infinity of -1 to the n does not exist. It goes 1, -1, 1, -1, 1, -1, 1, -1. But does not exist is not 0, so then it diverges at -1 by the ratio test, or by the divergence test. And if we did the limit as n goes to infinity of 1 to the n, well, that limit truly is 1, which is not 0, so it diverges at 1 also. So there you have that, and we just played with our knowledge of a geometric series to turn it into a power series. And I said here in red, here x is just playing the role of the radius in that geometric series formula. But we can do long division on this. And so I put the 1 minus x on the outside, and I put 1 on the inside. And then I say, well, 1 goes into 1 one time, and then 1 times 1 is 1, and 1 times negative x is negative x. And then I subtract, and 1 minus 1 is 0, and 0 minus negative x is a positive x. And then 1 goes into x times, and then x times 1 is x, and x times negative x is negative x squared. And we subtract, and then x minus x is 0, and 0 minus negative x squared is positive x squared, and so on and so forth. So you guys know how to do long division, but if you look, this is exactly what that turns out to be. And so that's kind of cool that you can generate that power series just using long division, and you're never going to get a remainder of 0, and so therefore it just goes on and on forever. So that was 1 over 1 minus x. What if we had something like 1 over 1 plus x? Then what do we do there? Well, how would you go from 1 over 1 minus x to 1 over 1 plus x? And the important thing here to note, guys, is this. The minus is part of that geometric formula. And so when I have the plus there, it's actually against what I know to be true already. So I could say this, well, 1 over 1 plus x is really 1 over 1 minus negative x. And then if I have minus a negative x there, then all I'm doing is I'm replacing x with negative x, and so I should replace a negative x up there. So watch how that happens. So here's the 1 over 1 plus x. We say it's 1 over 1 minus negative x. And then that replaces x with negative x in that geometric series formula. And then this I can break off as a negative 1 to the n and x to the n. This now, that negative 1 to the n, you guys know, alternates the series. And so it's now an alternating series. Negative 1 to the 0 is 1, but negative 1 to the first is negative 1, and so on and so forth. So this will come out to be 1, and then a minus 1, but an x to the 1, and then negative 1 squared is positive, and then we'd have x squared. Negative 1 cubed is negative, and then we'd have x cubed, and so on and so forth. So this is me generating it from this formula. But if you do the division, it works out to be exactly what it was up here. So, and I'm not going to go through that whole thing. So in this case, it converges when the absolute value of x is negative 1. But negative x is really negative 1 times x. And so I've done that. And then I used a property that the absolute value of a times b is equal to the absolute value of a times the absolute value of b. So I broke it apart here, and I know the absolute value of negative 1 is 1, and so it's the same radius of convergence. On this one, though, let me see what we have. When we put in negative 1, we get division by 0, and when we put in 1, so you're going to have to check it. The next one is a very famous formula. It's called Euler's formula. And the reason it's so cool is it relates an exponential function to trig functions. And the reason that this should seem really rather odd is that exponential functions usually look like this. And the big thing is they shoot to infinity. Sines and cosines, if it's cosine, it looks like this. And if it's sine, it looks like this. And so those never shoot to infinity, though. And this thing seems to shoot up to infinity. And so what's the deal there? And so if I wanted to prove this formula, you actually prove it using Taylor series. And so here's what it looks like. So if I want e to the I theta, all I have to do is take my e to the x and replace x with I theta. And so I've done that right here. Then everywhere over here, there's an x. I just put an I theta. So those are all in there. And then the thing that you have to remember is this, that I to the first power, so I'm going to even write this in here. So I to the first power is I, but wait, let me erase this, make it smaller. So I to the first power is I squared is -1, I cubed is -I, and I to the fourth is 1. And then that pattern continues. And so this will be just an I, but this will be I squared, which is a negative. And so that's where we get this negative down here. But then we'd have a theta squared there and a 2 factorial. And then you'd have I cubed, but I cubed is -I, so there's a negative, and I need my I in there, and I need my I in there. So here's what was missing in that. I to the fourth is 1, and so since I to the fourth is 1, we'd have a 1 and a theta to the fourth, and then over 4 factorial. And then we have the I to the fifth. I to the fifth then is just I. That's why I put that I there. And then we would have theta to the fifth over 5 factorial. And that pattern just keeps going. But notice this. In all of the odd powers, there is left an I in there. But all of the even powers, you have 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial minus theta to the sixth over 6 factorial. And the cool thing about that is the evens, that is cosine. So the 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, that you should know as cosine. And since that goes on forever and ever and ever, so there is a plus ... in there too, that gives you the cosine portion of it. And then because all of the odd ones had an I in them still, so we had an I there and an I there and an I there and an I there, I can pull the one I out, and that gives me a theta minus theta cubed over 3 factorial plus theta to the fifth over 5 factorial. And that I then stays, and this in here becomes sine theta. And so that actually shows the proof to why that formula is true. And it uses Taylor series, our knowledge of powers of I, and how we would break that apart into 2 different sums. So recall that last time we had cosine and sine, and then these are the ones that I'm comparing up here. So this I did last time for us. All right, what about a problem like this? So notice I know the Taylor series for e to the x. The Taylor series for x squared is just x squared because it is its own parabola. And so how would you go about finding this? Well, I know what e to the x is, and we've done it several times today. So if I want x squared times e to the x, I'm just going to put x squared and then what I know e to the x to be. And then all I have to do is distribute that x squared to every piece, and I get this. And then I see if I started at 2, then it would be 2 and 3 and 4, and okay, that works. And then this is almost 0 factorial and 1 factorial. So when it's a 3, it was a 1. When it was a 2, it was a 0. When it's a 4, it's a 2, and a 5, and a 3, and a 6, and a 4. Those differ by 2. And so that's how I wound up with that. And then you could take this and do the ratio test on it and figure out the radius and interval of convergence for it. Now, earlier in the notes, we learned this formula for just what we have from our knowledge of geometric formulas. But we know something cool. We know that the antiderivative of 1 over 1 plus x is ln absolute value 1 plus x plus c. And so in there, if I integrate that, well, if I'm going to integrate that integrand there, but that is equal to this, if I want to integrate that, it should be the same as integrating that. And so notice my c is there, and then I have this integral in there. So the antiderivative of x is 1. This gives me x squared over 2, and x cubed over 3, and x to the 4th over 4, x to the 5th over 5, and so on and so forth. It was alternating signs because we had to play that minus a negative trick. And so there's what I get for that. Now if I let x be 0, if x is 0, I get the ln of 1. And the ln of 1 is 0. So this side becomes 0. And on the other side, I have a c, so that's there. And then I have 0, minus 0, plus 0, minus 0, plus 0, forever. So that tells me c equals 0. And so then I have a formula now for the ln of 1 plus x. But I got it not by taking derivatives of this, and you don't want to do that, guys, because the first derivative is 1 over 1 plus x. The second is negative 1 over 1 plus x squared. Then we have 2 over 1 plus x cubed. And there's not really a good pattern that starts there. It alternates and it does some weird stuff. So, but this way of doing it, using our knowledge of antiderivatives, and then help us solve for that constant, gives us a Taylor series for that ln function. Now notice that ln 1 plus x is just the ln graph, and it's shifted left one. And so at negative 1, the value is negative infinity, and that it won't converge on that side. So no matter what, you can't even plug in negative 1, so it's not allowed. And then at 1, when you plug in 1, down, let's go back over here, in this, if I let x be 1, then this is gone. And this right here, without that x to the n, that is the harmonic series, the alternating harmonic. And the alternating harmonic converges. And so that's why we get the equal there. And so you could check it, though, at both endpoints. You could do the ratio test on it, and everything would work out. But here's how it really works if we were going to check it. So when I put in negative 1, I have a negative 1 there. That gives me a negative, and if same base to powers, you add the powers, and so n plus n is 2n, and then we have the minus 1 right there. And so then I can break this apart, and so x to the 2, or negative 1 to the 2n minus 1 is negative 1 to the 2n times negative 1 to the 1. And negative 1 to the 2n is always even, and negative 1 to an even is always positive. And so you're only going to get that negative 1 to the negative 1 power, which is negative 1. That negative 1 will pull out as a constant. This is the harmonic series, and the harmonic series diverges, and so at negative 1, it diverges, and that's why I don't have the equal sign there. Now, when we check 1, this is what I was saying before, when I plug in 1, this is just 1, and so I wind up with this, and this is alternating harmonic. And so I already know that it converges, and therefore it diverges on the negative 1 side, but it converges on the 1 side, or that interval right there. The final one, and this is cool for a number of reasons, it's to get the Taylor series expansion for arctangent. And arctangent has a really cool graph to it. It looks like the cubed root graph, something like that. It is asymptotic to pi over 2 and negative pi over 2, and it just runs between those bands. So, but I know if I take the antiderivative of 1 over 1 plus x squared, that is arctan x plus c. So, how do I build 1 over 1 plus x squared? Well, 1 over 1 plus x squared, remember, I need 1 over 1 minus r. And so I need to build that minus in there. That was the big thing from a number of pages ago. And so, but it's a plus. So I'm going to make it minus negative x squared. And so, then in the formula for geometric, remember the sum just x to the n, I'm going to replace the x with negative x squared. So there's that. The negative 1 to the n then pops out, and we have x to the 2n. If I write that out a little bit, there's what it looks like. And so then I know that arctangent is c plus whatever this antiderivative turns out to be. But this is nothing more than 1 over 1 plus x squared, just expanded out quite a bit. Hey, incidentally too, and I didn't do this in here, and I didn't even think about it at the time, but if you had 1 over 1 plus x squared, and you want to do something cool, do this, and do the long division, and it would come out to be that. So, this though, we've done it with the ln and the 1 over 1 plus x, and so, in this case, the antiderivative of 1 is x, then we get x cubed over 3 to the 5 over 5, 7 over 7, 9 over 9, and it alternates still, so we get that piece right there. So then I know what this looks like, so I can say it's the sum n equals, in this case, 0 to infinity. I was going to say 1 to infinity, but it's probably, I did this because it's the way it is in the book. But looking at this, watch this. If I had to write this in a different way, my first inkling would be to do this. I'd say, well, it's the sum n equals, and I'm going to say 1 to infinity. And in that way, if I'm just going here, it should be x to the 2n minus 1. And let's see if that works. So when it's 1, 2 times 1 is 2 minus 1 is 1, so you would get x to the 1. When n is 2, 2 times 2 is 4 minus 1 is 3. That would work. And then when n is 3, you'd get 6 minus 1 is 5. Okay, so that's working there. Then it starts with a positive, and so I know then I need a negative 1 to a power, but if I put the n power, negative 1 to the 1 is negative, and so it would start negative plus negative plus negative, and I don't want that. So instead, I'm going to offset that also. And then whatever this power was, that number matched. So that power, yeah, that's true. And so if the power is 2n minus 1, I would make that 2n minus 1. So this is an alternate formula for that piece, but the index starts at 1. And so it doesn't matter. But this one, see, you have the minus 1 and the minus and stuff. And this one you get pluses and then a nice n and a nice start. And so I think this one just looks more aesthetically pleasing. And so we went with that. Now, the arctangent of 0 is 0. And that implies that c is 0. And the reason is because if arctan is 0, you'd have a 0 here. But then that's 0, 0, 0, 0, 0, and so c equals 0. So we get that, and then now I have a complete Taylor series for arctangent, and I didn't have to take those derivatives. These derivatives are worse, because the first one is 1 over 1 plus x squared, or 1 plus x squared to the negative 1. Then you get negative 1 plus x squared to the negative 2 times 2x, and now it's a product rule. And so, or a quotient rule if you put that back to the bottom. So, taking derivatives of this and trying to brute force the Taylor series, Not a good plan. And it's not a good plan because them derivatives get so messed up. But using our intelligence and other knowledge, we can incorporate that into this Taylor series idea, and it works out. I wrote down here the interval and radius of convergence, but you could do this and use the ratio test on it, and you would find this exact bit of information. So I hope that helps, and that's my explanation. The last page is blank, and so try to have fun with this. Read the section though. Like, I didn't cover everything in here. There is a theorem about if you manipulate a series, the radius and interval of convergence will be the same as the original one, and that's why, like, because e to the x converges for all x, e to the x squared is going to converge for all x, and e to the 2x, if you did 2x, there would be a 2x in there, and that would be a 2 to the n, x to the n over n factorial, but it's going to have the same interval and radius of convergence. So there are some theorems like that. There is a lot with this geometric formula. They'll do stuff like 1 over 1 plus 3x, and then you have to, that changes the radius of convergence, because then that's 1 over 1 minus negative 3x, and then your r is like negative 3x, and so then you would need negative 3x to be less than 1, and then negative 3 makes it to be a third, or whatever it is. So if you have constants in here in front of the x, it tweaks this radius of convergence for it. And it's kind of cool to see. And then there's the tricks of using the negatives, and then there's the tricks of like writing one Taylor series and trying to branch it out into a combination of other ones. And then there's ones about, well, what if you multiplied a known Taylor series by just like an algebraic expression? And there's things to go about that. And this won't change the radius or interval of convergence either. And it's because x squared is its own Taylor polynomial, so we don't have to worry about it. And then the integral thing, it's important that c comes with it. You know, it always had to be there. And if you took 1a with me, I took points from you for doing that and leaving that off, and it's partly this reason, because we had to check it every single time, and we did it for the ln, and we did it for the arctangent one right here. So we had to play that trick both times. All right, that should get you through the homework. That is my explanation. That's a little faster than I would have done it in class, but hopefully you can see what I was thinking, what I was saying, what I meant. And an important thing is, at the time, I didn't notice that I was missing i's right there. And so there is a mistake in the notes. All right? But I will fix them and take care of that. Okay? Hang in there, guys. I'm proud of you, and we'll talk soon. Okay? Bye-bye.